The so-called knapsack problem is another famous thought exercise in computer science. Here we have a theoretical knapsack with a limited weight capacity and more items than can possibly fit in it. Each item has a weight and a value. The question here is, how can I optimize the total value of items in my knapsack given the weight constraint? We'll focus on the 0-1 knapsack problem, where you only have one of each object and you must either take or leave a whole object. In some other variants, you can take a fraction of an object. When I heard about this problem, my first thought was, just put the objects with the highest values in first. But what if putting the two elements with the highest values hit the weight limit, but putting all the other elements in together would actually fit and have a higher value? There aren't a lot of actual knapsacks in computer science, but this problem describes an optimization issue that crops up often. Before devising the best solution, particularly if you're stuck, it can be helpful to think of the solution that's slow but straightforward. Here, we could try every combination of objects and just pick the one that's best, also called the brute force solution. The runtime of this solution is on the order of 2 raised to the n, where n is the number of objects. There are actually 2 to the n possible combinations. There's a precise mathematical reason for this, but you could also think of one combination as a string of length n, where each spot has a 1 if it's in the knapsack or a 0 if it's left out. That means this is an exponential time algorithm, since the n is an exponent. We would prefer a polynomial time algorithm, where the n is multiplied by something else or has a constant number for an exponent, which is going to be much faster for large numbers. Let's talk about a smarter approach. Our first goal doesn't need to be maximize the value for the largest weight possible. What if we tried to maximize the value for the smallest weights possible, then kept adding them together until we had our maximum weight? Let's look at an example. We start by creating an array, which we'll use to store the maximum possible value for every weight up into our weight limit. We assume that the weights are all positive integers, so the indices in the array represent those weights. We initialize everything to 0 for now. These are our objects that we're trying to fit in a knapsack with a weight limit of 6. We take out the object with a weight of 2. We can update the value at index 2 to the value of the object. Then we'll update everything after it as well with the same value. Even if our knapsack can hold 6, we've only seen one object so far, so we need to base that best value off one object. We look at the next object. Again, we can't change anything until index 5. The value of this object is bigger than the max, and it takes up the whole weight, so we replace the max value for weights 5 and 6. For the last object, the first thing we could possibly change is index 4. This value is less than that one, so we leave it alone. We look at index 5 and compare it to our value plus the value at index 1. Since the old value is larger, we leave it as is. At index 6, we add our object value to the value at index 2 and end up with a bigger value, so we replace it. And we've solved the problem. This may seem unnecessary with an example this small, but imagine how much time we'll save with lots of objects. Here, we're taking advantage of the table to store pre-computed maximum values. So we only need to do the work once to get those numbers. We go through every object and check if it can increase the maximum value of every possible weight up to our maximum weight. Thus, the runtime is n times w, where w is the weight limit of our knapsack and n is the number of elements. This is a pseudo-polynomial time solution. A true polynomial runtime wouldn't have a variable besides n. I reiterate, polynomial time algorithms are much faster than exponential time algorithms for big numbers, so the solution here is generally faster. The knapsack problem shows the beauty of a technique called dynamic programming. With dynamic programming, you can make a really complicated problem like this one run much faster by breaking it into subproblems. Here, the subproblem was finding the answer for a smaller weight. You begin by solving for something like a base case, a subproblem so small that the answer is very simple or trivial to compute. We started with one object. With only one thing to consider, finding the maximum possible value for any weight was simple. Another common feature of a dynamic programming solution is a lookup table that stores solutions to subproblems. We stored the maximum values for different weight limits in our lookup table. Dynamic programming solutions take advantage of these two things: solving the problem for a trivial case and storing the solution in a lookup table, by using them to slowly add complexity to a problem. Another feature of a dynamic programming solution is an equation used at each step as you add complexity. For us, the equation looks something like this. The equation often combines some values previously computed in the lookup table, sometimes with each other and sometimes with a new value you introduce, like the value of whatever object you're looking at. We used the values already stored in the table as we added new objects, a technique often called memoization, so we ultimately didn't need to recompute them every time. This is the hidden power of dynamic programming. You compute and save solutions to smaller problems, then you don't need to calculate them again for more complex problems. It might seem like a simple idea, but it can have a really powerful effect on efficiency if it's done well. One of the most useful skills to have when going into a technical interview is the ability to spot a problem that has a dynamic programming solution. It didn't come naturally to me at first, but after practicing by trying to solve a bunch of dynamic programming problems on my own, I started to get the hang of it. One thing you need to look out for is a complicated problem that seems to require trying every combination to find the solution. You need to ask yourself, can I break this problem into subproblems? If the answer is yes, then you've got a problem with a dynamic programming solution.